Welcome back guys to my YouTube channel. Today we will solve the numericals of class 12th physics chapter 13 AC circuits. So let's look at the first sum. If the effective current in a 50 cycle AC circuit is 5 ampere, what is the peak value of current? What is the current for 1 by 600 second after it was 0? So solution, here they have given us the effective current in a 50 cycle AC circuit is 5 ampere. That is, for frequency 50 hertz, the effective current, that is the RMS value of the current, IRMS, is equal to 5 ampere. So whenever we are talking about any effective value in an AC circuit, that means we are talking about the RMS value, and it is also equivalent to its DC value. So here they want us to find out the peak value of current, that is I naught. Now we know that I naught is equal to IRMS into root 2. So IRMS is given to us as 5 ampere into root 2, we know it is 1.414. So 5 into 1.414 is 7.07 ampere. So the peak value of current is 7.07 ampere. We also need to calculate the current for 1 by 600 second after it was 0, that is the instantaneous current at a time t equal to 1 by 600 second. So the expression for instantaneous current I equal to is I naught into sine omega t. Now we know the value of I naught. We need to find out what is omega, and t is 1 by 600 seconds. So we know omega is equal to 2 pi f, and f is 50 hertz. So omega will be 2 pi into 50. From here we can write omega equal to 100 pi. Now the I current can be written as I naught, which is 7.07 into sine of omega t, that is sine of omega, which is 100 pi, and t is 1 by 600. So 100 ones are 100 six are, then this thing comes out to be pi by 6. So 7.07 into sine of pi by 6. Now sine of pi by 6 is half. So I can be written as 7.07 divided by 2, which comes out to be 3.535 ampere. So the instantaneous current at time 1 by 600 second is 3.535 ampere. I hope you understood this sum. Let's look at the next sum. A light bulb is rated 100 watt for 220 volt AC supply of 50 hertz. Calculate a resistance of the bulb, and second the RMS current through the bulb. Now whenever we are talking about the value of AC supply, it is mostly its RMS value. So here they have given us the ERMS value, which is equal to 220 volt, and power, which is equal to 100 watt, and we need to find out the resistance of the bulb. So we know that power is equal to ERMS into IRMS. Now IRMS can be written as ERMS into ERMS upon R, that is IRMS is ERMS upon R. So this thing becomes power equal to E square RMS upon R. So we know the value of ERMS, we know the value of power, we can find out the resistance. So R can be written as ERMS square divided by P. So ERMS is 220, and ERMS square will be 220 into 220, and power is 100. So 100, these two zeros get cancelled. 22 into 22 is, we get R equal to 484 ohms. Next thing, they want us to find the RMS current through the bulb. Now we know that IRMS is ERMS upon R. So IRMS can be written as ERMS upon R, which comes out to be 220 divided by 484, which is equal to 0.4545 ampere. So IRMS is equal to 0.4545 ampere. Let's look at the next sum. A 15 microfarad capacitor is connected to a 220 volt 50 hertz source. Find the capacitive reactance and the current, both RMS and peak in the circuit. If the frequency is double, what will happen to the capacitive reactance and the current? So first thing first, we need to find out the capacitive reactance. Now capacitive reactance, that is Xc, is given as 1 upon omega c. So we know the value of C, which is C is given to us as 15 microfarad. which can be written as 15 into 10 raised to minus 6 farad, and omega is 2 pi f. So omega can be written as 2 into 3.14 into f is 50 hertz. Okay, so 2 into 50 is 100, and 100 into 3.14 is 314 radian per second. Okay, so we can find out xc equal to 1 upon omega, which is 314 into c, 15 into 10 raised to minus 6. So the value of xc comes out to be 212.3 ohms. Another thing they want to find us is the current, both RMS and peak value. So for a pure capacitive circuit, we know that IRMS is equal to ERMS upon XC. So ERMS is given to us as 220 volt, and XC we found out to be 212.3 ohms. So calculating this, we get IRMS as 1.036 ampere, which can be also written as 1.04 ampere. Now to find out peak value, we know that I naught is equal to IRMS into root 2. So IRMS is 1.04 and root 2 is 1.414. Now multiplying this, we get I naught is equal to 1.47 ampere. So in the next part of the question, they have asked us that if the frequency is double, what will happen to the capacitive reactance and current. So we know that capacitive reactance is given as Xc equal to 1 upon omega c. In terms of frequency, this thing can be written as 1 upon 2 pi fc, which implies that Xc is inversely proportional to frequency. So keeping that in mind, if frequency is doubled, let the new frequency f dash be equal to twice the old frequency, and let the new capacitive reactance xc dash be equal to 1 upon 2 pi f dash c, which can be written as 1 upon 2 pi 2f into c. Now taking 1 by 2 outside, this thing comes out to 1 upon 2 pi fc. Now 1 upon 2 pi fc is nothing but our xc, our old capacitive reactance, which implies we can write xc dash, that is our new capacitive reactance when the frequency is double, is equal to half the old capacitive reactance, which implies that when frequency is double, capacitive reactance is halved. Now talking about current, we know that IRMS is equal to ERMS upon XC, which can be written as ERMS upon 1 upon omega c, which is equal to omega c into ERMS, correct? And omega can be written as 2 pi f c into ERMS. Now when frequency is doubled, same thing, which implies that our new current IRMS dash will be equal to 2 pi f dash c into ERMS. Now f dash, we know that it is 2f, so again this thing comes out to be twice the old current, which implies that when frequency is doubled, the current is also doubled. I hope you understood this sum. Let's look at the next sum. An AC circuit consists of only an inductor of inductance 2 Henry. If the current is represented by a sine wave of amplitude 0.25 ampere and frequency 60 Hz, calculate the effective potential difference across the inductor. So solution, they have given us an inductive circuit, that is a pure inductance circuit, for which the inductance L is equal to 2 Henry and the current is represented by a sine wave of amplitude 0.25 ampere. That is, we know I is equal to I naught into sine omega t, and this is the amplitude of current, which implies that they have given us the peak value of current, which is equal to 0.25 ampere, and frequency to be 60 hertz. So we need to calculate the effective potential difference. Whenever we are talking about effective potential difference, it means the RMS value. So we need to find out ERMS. So in order to find out ERMS for an inductive circuit, we know that E naught is equal to I naught into XL. So we know the value of I naught, we need to find out XL. So XL can be written as omega L, and omega is 2 pi f, so 2 pi f into L. Now this thing can be written as 2 into 3.142 into frequency which is given to us 60 hertz into L, which is 2. So calculating this, we get XL equal to 75.36 ohms. Now putting this value here, we get E naught equal to I naught, which is 0.25 into XL, which is 75.36 ohms. So E naught comes out to be 188.4 volts. Now this is the peak value of potential difference. We need to find out the effective value, that is ERMS. Now ERMS is equal to E naught upon root 2, which is equal to 188.4 divided by 1.414, which is equal to 133.22 volt. So the effective potential difference across the inductor is 133.22 volts. Let's look at the next sum. Alternating EMF of E equal to 220 sine 100 pi t is applied to a circuit containing an inductance of 1 by pi Henry. Write an equation for instantaneous current through the circuit. What will be the reading of the AC galvanometer connected in the circuit? So solution, we have been given the expression for instantaneous EMF, which is equal to E equal to 220 sine 100 pi t. Comparing it with the expression of EMF E equal to E naught into sine omega t, we get E naught is given to us as 220 volt and omega is given to us as 100 pi. They have also given us L, which is equal to 1 by pi Henry, and we need to write the equation for instantaneous current. Now we know equation for instantaneous current is given as I equal to I naught into sine omega t minus pi by 2, because for an inductive circuit we know that current lags behind the EMF by 90 degree. So this is the expression for instantaneous current. Now we need to find out first of all I naught. So to find out I naught, we know that I naught is equal to E naught upon XL. So first we need to find out XL. Now XL can be given as XL equal to omega L, and omega is already given to us as 100 pi. So 100 pi into L is 1 by pi. So pi gets cancelled and XL comes out to be 100 ohms. Putting the value of E naught and XL, E naught is given to us as 220 volt and XL we found out 100 ohms. So 0 get cancelled and 22 divided by 10 is 2.2 ampere. So I naught is equal to 2.2 ampere. So writing the expression now, I is equal to 2.2 into sine omega is 100 pi t minus pi by 2. So this is the expression for instantaneous current through the circuit. We also need to find out the reading in the AC galvanometer connected in the circuit. We know that the galvanometer will record the effective current, that is the RMS current in the circuit. So for calculating the RMS value of current, we know IRMS is equal to I naught by root 2. So I naught is 2.2 and root 2 is 1.414. This thing comes out to be 1.55 ampere. So the galvanometer will record the reading 1.55 ampere when it is connected in the circuit. I hope you understood this sum. Let's look at the next sum. A 24 microfarad capacitor, a 0.1 Henry inductor and a 25 ohms resistor are connected in series with an AC source whose EMF is given by E equal to 310 sine 314 t. What is the frequency, reactance, impedance, current and phase angle of the circuit? So solution, we need to find out what are frequency, reactance, that is XL minus XC value, then impedance Z, then current I RMS value, and phase angle phi of the circuit. So we have been given the capacitance, inductance and resistance. So this is a series LCR circuit. So we know capacitance is 25 microfarad, which can be written as 25 into 10 raised to minus 6 farad, and L is given to us 0.1 Henry. Also R is given to us 25 ohms. So first of all we need to find out the frequency. Now frequency is given by F equal to omega upon 2 pi. So from the expression for instantaneous EMF E equal to 310 sine 314 t, comparing this with the expression E equal to E naught sine omega t, we can say that E naught is 310 and omega is 314. So putting this value of omega here, we can say that omega is 314 divided by 2 pi. So solving this, we can get 314 divided by 2 into 3.14, which is equal to 50 hertz. Correct? So frequency is 50 hertz. Now to find out the reactance in the circuit, we need to find out XL and XC. So XL is given as omega L, which is equal to omega, which is 314 into L, which is 0.1. This thing comes out to be 31.4 ohms, and XC is equal to 1 upon omega C, which is equal to 1 upon 314 into C. C is 25 into 10 raised to minus 6. So calculating this, we get XC equal to 127.38 ohms. Now the total reactance in the circuit, that is XL minus XC. XL minus XC is given to us as 127.38 minus 31.4 ohms. This comes out to be 95.98 ohms, which can be written as 96 ohms. So the reactance of the circuit is 96 ohm. Also we need to find out the impedance. So Z is given to us as root under R square plus the reactance, that is XL minus XC square. So putting the value of R square and the reactance that we got, R square is 25 square, which is 625, plus XL minus XC, that is 96. So 96 square is 9216. So adding them, we get 9841. Now taking root, we get Z equal to 99.2 ohms. Now what is remaining is the IRMS value and phase angle. So IRMS is given as ERMS upon Z. This formula is only for the series LCR circuit. So we don't know the value of ERMS, but we know what is E naught from this expression. So ERMS is equal to E naught upon root 2, and E naught is given to us as 310 volts and root 2 is 1.414. So solving this, we get ERMS equal to 219.17 volt. So IRMS will become 219.17 divided by Z, which is 99.2 ohms. So solving this, we get IRMS equal to 2.21 ampere. Now let's find out the phase angle, which is given by the formula tan phi equal to XL minus XC divided by R. This implies that phi is equal to tan inverse of XL minus XC divided by R. So putting the value of the reactance and resistance, XL minus XC is 96 and resistance is 25. Now solving this and calculating the tan inverse of this value, we get phi equal to tan inverse of 3.84. Now calculating the tan inverse, we get phi equal to 75.4 degree, but we need to find out it in radians. So 75.4 into pi by 180. Solving this, we get phi equal to 1.315 radians. I hope you understood this sum.